Good afternoon, ladies and gentlemen, and welcome to Energy for Development Stream 2. My name is Xique-Xique, and my colleagues and I today will be talking to you about what makes a sustainable community. Now, the UN Sustainable Development Goals provide a very clear pathway towards a more sustainable future for populations all around the world. However, in order to meet these goals by 2030, there is still much work that needs to be done. So today we'll be talking to you about some specific goals. And in order to help us do that, we would like for you to meet Mark. Now, Mark is a pragmatic and passionate individual who really has a drive to solve some of the world's most complex challenges. He's just graduated with a degree in engineering and has now decided that he's going to use his newfound skill set to help his native country of SEF land, which has had its fair share of challenges surrounding development, move towards a more sustainable future. Now, in order to do that, he started thinking about what are the key challenges that are hindering progress towards a more sustainable future. And he came up with 5 key challenges. These include the accessibility and affordability of technology, but also a lack of domestic technical knowledge. He also highlighted lack of policy support from government and high perceived financial risk with investing in projects in SEF land. When looking at individual SDGs, he thought that through addressing SDG 7, which is access to affordable and clean energy, he would be able to address a number of other key issues affecting residents of SEF land, such as access to clean water and resilience to the future impacts of climate change. So to look at some of these SDGs in detail, Mark enlisted the help of some associates. So today you will hear from each of those associates and they will talk to you about the work they have been doing over the past few months. So I will firstly go on to talk to you about battery degradation in mini-grids. Matthias will then talk to you about how machine learning can be used to improve demand estimation in communities that have never had access to electricity. Paloma will then talk to you about how electricity can be used productively to generate income and alleviate poverty. Camille will then talk to you about how photovoltaics can be used in groundwater pumping. And then Anne will talk to you about the sustainability of such approaches. We will then touch on organic solar cells, with Wesley talking to you about how these can be used in food production and to produce hydrogen. Finally, Daniel will talk to you about the challenges involved with developing and using new technologies. So I'd like to talk to you now about how insights from degradation modelling can be used to improve the lifetime of batteries in mini-grids. Mini-grids are expected to play an increasingly significant role in achieving universal energy access. Not only do they enable basic access to electricity, they also allow the use of higher powered appliances that can be used for income generating activities. As you can see from the figure on the slide, batteries are often a major cost component of mini-grids. Therefore, increasing their lifetime to reduce the frequency of replacement will help to increase the financial viability of mini-grids. In order to extend the lifetime of batteries, you first need to understand the conditions that accelerate degradation. For example, in the case of lithium-ion batteries, high ambient temperatures and high state of charge are both conditions that will accelerate the rate of capacity fade. Derating strategies involve limiting the performance of a device, such as a battery, in order to prolong its lifetime and to ensure safety. These algorithms can be easily implemented in energy management systems without any need for auxiliary equipment. However, if you limit the operation of a system, there will be cases where you may not be able to fulfill all demand. So the question must be asked, what are the implications of derating on system reliability, emissions intensity, and the cost of electricity? To answer this question, a detailed battery degradation model and mini-grid planning software called Clover were used to investigate the impact of derating for case studies in Rwanda and India. When performing the degradation analysis, it can be seen that calendar aging, which occurs even during the battery's rest state, is the most significant aging mechanism. Cycle aging was found to be much less significant due to low currents at the case studies. When comparing results between the degradation model and Clover, it was found that Clover often underestimates and overestimates the extent of capacity fade. Therefore, it can be said that by including a more detailed degradation modeling in Clover, more optimal system sizes could be achieved. When looking at the impact of derating, it was found that state of charge derating was able to increase battery lifetime by over 11 years. This actually increased the end-of-life condition, pushing it outside of the 20-year simulation period. When looking at the impact of temperature derating, these were less significant but still led to a maximum of 2.3 years lifetime extension. Increases in the unmet energy fraction and the blackout frequency were seen, however these are relatively small and did not impact the emissions intensity or the LCUE. Therefore, it could be said that MARC could use derating strategies in order to prolong the lifetime of batteries in mini-grids in SEF land. Thank you very much for listening, and I will now hand over to my colleague Matthias.
Hi, thank you very much, Jake. So as Jake talked about batteries, one of the key components in mini-grids, my name is Matthias Jean, and I am now going to talk about demand forecasting in mini-grid rural electrification. So it is often very complicated to forecast what will be the energy demand of a school or a village which doesn't have access to electricity yet. That's why demand estimation is a crucial step in electrification projects, and improving it could lead to huge cost reduction by avoiding oversizing while improving system operation and reliability. For my thesis, I worked in partnership with OVO Foundation, the foundation of OVO Energy, a British energy supplier, and Energy for Impact, which is an NGO helping the development of energy companies in sub-Saharan Africa. Project JUA aims to provide electricity access to schools and clinics in the poorest counties of Kenya. The goal is to install off-grid systems with solar PV and battery packs to 320 institutions by the end of 2020. I had access to data from 170 institutions, which have already been equipped. For every site, I have utilization data, that is the production, the consumption, and the battery voltage, and also objective data, namely the number of students, the number of patients, or the size of the school or of the clinic, etc. The first step was to understand and analyze production and consumption patterns. To do so, I studied the variables over different timescales to observe and understand different phenomena, such as, for example, the impact of holidays, the impact of closing days, of seasonal effects, or even of behavior changes. Then, I studied the Hourly profile, which is a very interesting metric. Looking at the production, there is no production at night and a peak production at around midday, which seems pretty coherent with what is expected. Concerning the production, it is more complicated to understand. It seems to be higher at night, which can be explained by the large share of power dedicated to the lighting. The utilization rate is equal to the power consumed divided by the power produced. Depending on this value, the system sizing can be assessed. A small utilization rate means that the full potential of the installation is not exploited. On the contrary, a high utilization rate shows a great operation of the system. It is hard to know whether the utilization rate is high because the system is correctly sized or because it's undersized. That's why it is crucial to discuss with the beneficiaries, to have feedbacks about the utilization of the system, and to determine whether the system is undersized or correctly sized. The distribution presented here shows that, for most of the schools electrified during Project JUA, the installation had been largely oversized. The final idea of my thesis was to do demand forecasting. Indeed, for every institution, I had access to both utilization data and objective data. That's why the use of machine learning, which is able to link objective criteria with consumption data, seems to be relevant here. Due to the limited amount of available data, the results remained limited and experimental. However, it indicates a clear potential for future researchers with more complete datasets. Finally, the study identified several opportunities linked to the utilization of data for electrification projects. It can be used to do fault detection, to quantify the amount of electricity wasted for every institution, or even to improve demand-side management of the systems. Concerning demand forecasting, further researches with more robust datasets could lead to a huge cost reduction in mini-grid electrification. Thank you very much for listening, and I will now let my colleague Paloma talk about how to develop a productive use of this electricity.
Thank you, Matthias. Well, so far my colleagues discussed some important factors that Mark will have to consider to make sure that SEF land will have financial sustainability in the long term. But the question still remains on how can he ensure that the community will have the ability and willingness to pay for electricity. So in order to do that, it is essential that economic growth is promoted in the community. But how can we do that? So I will discuss today a case study of a remote community in the semi-arid region of Brazil. This region has a particular challenge of water scarcity with cyclic droughts, and this condition affects the main income source in the area, which is the livestock production. Also, the community profile is low income, with almost 90% of the families living below the minimum wage. And although some of the families already do have access to electricity, they only have a solar system with limited capacity, so this ends up hindering the use of agricultural machinery. So as Jake previously mentioned, solar microgrids can be a very good alternative to enable productive uses of energy. In this particular case, electricity can be used to power water pumps and to power the equipment necessary to produce and to store livestock feed in the periods of rain. So the community will still have water and food available when it comes to droughts. It can also be used to power equipment in secondary activities such as the honey production, enabling adding value to the product and also increasing the speed of the production. This project will be implemented by the local energy utility, so they must comply with a series of Brazilian regulations which does not necessarily correspond to the most cost-effective solution. In fact, these regulations, they are focused to ensure a secure supply to all consumers, requiring a minimum size of batteries and of the solar system. So this will in turn have an impact on the other pillars of the energy trilemma, namely the affordability and the environmental sustainability. So the question I want to answer is, what are the implications of meeting these Brazilian regulations? For that, I simulated three scenarios. The first with a solar microgrid using only batteries, and the second using batteries and diesel, both meeting the country's regulations. I will then compare these solutions with a third, an optimized case that would still meet the demand. And also, according to the data provided by the local energy utility, I built two load profiles that will be compared to estimate the impact on costs of wrongly forecasting the demand. Now, observing the results, we can see that the levelized cost of used electricity when meeting the Brazilian regulations is much higher than the optimum solutions, with the initial investment for the system with only batteries being almost twice as much than the latter. So this may lead to delays in the universal energy access targets, or even a choice of system that would hinder the use of farming machinery, which is essential to produce economic growth to the community. Now, considering the benefits for the consumers, the expected return can correspond to up to 5 times the minimum wage per farmer in a year, a value that is very significant for families in conditions of poverty or extreme poverty, which is the case of this community. In addition to that, the investment per consumer is expected to bring a similar benefit in terms of revenue for the producer, so it is essential that productive uses of energy are considered when designing the system, tackling both SDGs 1 of poverty alleviation and 8 of decent work and economic growth. Interestingly, the best solution in terms of costs and emissions to meet the Brazilian regulations is the option with both batteries and diesel as backup. This counterintuitive result occurred because the battery system is highly oversized, with an average state of charge above 50%, so the diesel generator will hardly ever be used. This refers to what Jake previously said about the trade-offs between oversizing the storage system and increasing its lifetime. Unfortunately, this is a challenge for this specific case since the high upfront cost of having an oversized storage system hinders its development. In addition to that, when it comes to the risk of forecasting demand incorrectly, I observed a 30% increase in costs and emissions when comparing the optimum solutions for both load profiles, which shows the importance of using more accurate methods to forecasting demand, as Matthias previously mentioned. And finally, the economic benefits for the consumers are considerable, but that can only be achieved if the government provides not only financial support, but also technical support to the community. Thank you very much for listening, and I'll now hand over to Camille.
Thank you, Paloma. So my name is Camille, and I have worked on how to improve water access for communities in developing countries like SEF land. Indeed, the Sustainable Development Goal number 6 of the United Nations is to achieve a universal and safe access to drinking water for all by 2030. But today, still 11% of the humanity have no access to such a source of water. Photovoltaic solar pumping system could be a solution for this population to have access to water, even if they are not linked to electricity grid. But even if it is a technical solution, in fact, it is not accessible for all communities because it is very expensive, and the system also have viability problems. The conventional architecture for solar pumping system is with a tank storage. So there is a PV array connected to a motor pump, and when there is sun, the motor pump can pump water in a tank. People can collect water at every time in a day, even if there is no sun, because there is always water in the tank. I have studied an innovative architecture with battery storage in order to try to increase the accessibility of this system. So in this new architecture, there is not anymore tank, but there is a battery storage bank. And then the population can still have access to water at every time in a day, because if there is no sun, the pumps can still work with the electricity stored in the battery bank. I have compared this architecture on 3 criteria. The first one is technical, so how these two architectures satisfies the water demand of the different communities. The second one is economic, so what is the life cycle cost of each system? And the last one is social, what are the viabilities of these two systems? So I have done a techno-economic optimization in order to find the minimal life cycle cost of each system while they totally satisfies the water demand of the communities. And then I have analyze the difficulties of maintenance of the different systems. I have found that for the same satisfaction of demand, the life cycle cost of the tank architecture is 2 times higher than the life cycle cost of the battery architecture. This difference of price is mostly due to the difference of price of the storage devices, as you can see on the graph. So if we talk about money only, about affordability, the battery architecture is far more accessible for poor communities. However, we are not talking only of poor communities, but also of isolated communities, and the use of batteries raises other challenges. We need to regularly replace the battery bank, in fact 4 times, because every 4 years, so 4 times during the whole lifetime of the system, and if this replacement are not made, the whole viability of the system is threatened. So the pumping system storing electricity in battery can be 2 times cheaper than pumping system storing water in tank for the same satisfaction of demand. But the use of battery raises viability challenges because of the regular need of replacement. So in conclusion, it is necessary to develop operation and maintenance local schemes so the local population can take care of the maintenance and the replacements of the pumping system. And then with these schemes setting up, we can use this innovative architecture and we can increase the accessibility of photovoltaic solar pumping systems and improve the water access of poor and rural population. Thank you for listening. I will now hand over to Anne.
Thank you, Camille. So now we've established that solar pumps are a great way to increase water access, especially in off-grid areas. What we now want to make sure of, because as Camille said, the upfront costs can be very high, we want to make sure that they will last a long time once they're installed. Now, how do we make sure that the solar pump, once it's installed, will last a long time? The main risk is that when you pump, you're going to extract water from a borehole, and the water level in the borehole will decrease as you pump. And so we want to make sure that the water level in the borehole will always remain high enough to prevent any damage to the pump and to prevent any sudden stop in the water supply. The way we do that is we create something we call a borehole model that will really model the response of the water level in the borehole to pumping. The borehole models are created using pumping tests. So you pump, you see the effects it has on the water height in the borehole, and from that you create the model. Now, because we already have models, why is that a problem for us and with solar pumps? Well, basically, the pumping tests that are currently being done require a constant flow rate for a certain duration. And because we have solar pumps, we can't have constant flow rates because the flow rates will really follow the curve of the sun. If you look at this graph, you can see the irradiance over 2 days. And now if you look at the second graph, over the same 2 days, you have the values of the pumped flow rates, and they're directly proportional to the irradiance. So we can't use the classic pumping tests to train the borehole models. And because of that, the models are done and trained initially before the solar pump is installed, but then it's just kept that way and it's never recalibrated, even though the borehole might change in behavior. The question from there is it even possible to use solar pumping data in order to train a borehole model? The answer is yes. That was one of my first tasks. I tried different models, and you can see here the results for one of the models. This one actually reached an accuracy of 97%. So quite accurate models to predict the water height in the borehole. Now that we know we can use solar pumping data to train a borehole model, it means that we can design a solar pumping test. How would that work? Simply over a day, you would just collect the pumping data from the regular use of the pumping system. Use that data to train the borehole, and this would recalibrate regularly the model that you have. This means that you can detect early on any problem that you have with the pump or with the borehole before it's too late, meaning before it either halts completely the supply in water or before you have to do any very expensive maintenance operations. So what does this mean for Mark? Well, simply that he can install a solar pump in his community with the guarantee that he will be able to track the borehole's health throughout its lifetime. Now I'll leave the rest to Wesley.
Thanks, Anne. Hi, everybody. My name is Wesley, and today I'll be talking to you about semi-transparent organic solar cells, or STOSCs. So, when Mark first approached me, he mentioned the need for more sustainable solar power for SEF land. He said he was considering organic solar cells as they are cheaper and greener to make compared to conventional solar cells. More importantly, he said that these solar cells could be made semi-transparent, which he thought could have potential in photovoltaic greenhouses that essentially generate power without compromising crop yields. He was also interested in using these cells in what's called unassisted photoelectrochemical water splitting systems. These systems essentially consist of a solar cell and a PEC cell, which are connected in series and split water using only sunlight, thereby producing hydrogen, which can then be used for heating, power, or energy storage. However, I found out that not much is actually known about how viable these semi-transparent organic solar cells are in these applications, which then spurred my research that looked into modeling the two applications to evaluate their viability. So, for water splitting systems, I first looked into comparing the solar to hydrogen or STH efficiencies of systems that use semi-transparent organic solar cells to systems using opaque organic solar cells. For this, I paired 15 different solar cells to a PEC cell that utilized a popular earth-abundant material hematite in two different configurations, back illumination and front illumination.
I then wanted to see whether it was even possible for such a system to realistically achieve the 10% STH efficiency required for commercial feasibility. So, what I did was I took the most efficient configuration from the first study and varied different parameters to see how good these devices have to be in order to do so. As for the PV-Greenhouse study, I basically modeled and evaluated the growth factor and power conversion efficiencies of 7 different semi-transparent organic solar cells and compared that against conventional PV greenhouse strategies which use opaque solar cells such as CIGS or silicon in a partial shading configuration. Moving on, from the results of the first study on water splitting systems, I found out that semi-transparent solar cells typically perform worse than their opaque counterparts due to how sensitive the PEC cell performance is to overlapping absorption profiles between the two components. Systems using opaque solar cells face less of such a constraint as sunlight reaches the PEC cell first in this case, allowing it to perform optimally. The solar cells, on the other hand, perform suboptimally but are still good enough to achieve a better STH efficiency due to the generally high performance that solar cells have compared to PEC cells. For the second study, I found that it was indeed possible to produce 10% STH efficiencies with a hematite-based system paired with either a single junction or a tandem solar cell. However, these components will need to have near-perfect properties which would be difficult to achieve in practice. Overall, this means that 1. Semi-transparent organic solar cells aren't viable for such an application unless you need the entire water splitting system to transmit light. And 2. Research efforts should probably shift to a different earth-abundant material or focus on other strategies to achieve commercially feasible solar hydrogen production. Moving on to the PV greenhouse study, it was shown here that the best performing semi-transparent organic solar cell could outperform CIGS solar cells and was even able to compete with silicon solar cells if transparency in its auxiliary layers were increased. However, it was noted that with recent advances in materials, there seems to be a trend towards using more absorptive active layer materials, which makes sense from a power generating perspective, but by doing so, these layers must be in turn made extremely thin to maintain the same transparency, which is problematic for large-scale manufacturing. So, what does this all mean? Well, it shows that semi-transparent organic solar cells are indeed viable in such an application, but moving forward, research efforts should focus more on increasing device transparency and manufacturability while maintaining a reasonable power conversion efficiency. Overall, this gave Mark a lot to think about regarding organic solar cells, which led to him eventually consulting my colleague Daniel on the fundamentals of organic solar cells. Daniel will tell you more about this. Daniel, please.
Thank you very much, Wesley, and hello everybody. My name is Daniel, and I was also approached by Mark after consulting Wesley. He was wondering why these solar cells were not present everywhere despite being such a promising technology. I told him that even though these cells have been known since the 1950s, which is quite a while ago, some of their fundamental processes are not quite really understood yet. I'll guide you through my research that studies the performance of these cells at low temperatures. This has to be accounted for when considering these devices for the sustainable community in SEF land. As Wesley mentioned, their stability and efficiency are not even comparable to that of their organic counterpart. To understand why, I had to investigate the working principles that govern the photocurrent generation in these devices at both an atomic and a molecular level. In simple terms, I had to study 5 main processes. First, a photon has to interact with an electron which, after being excited, generates a hole. Due to the interaction between molecules, the per electron hole remains bounded, creating an exciton that cannot dissociate at room temperature. Secondly, this exciton can diffuse through the molecular lattice of the organic semiconductor. If it finds another material with lower energy levels, the electron will jump to it, and the per electron hole now is still bounded, but the charge carriers coexist in different parts of the material. This is called charge transfer state or CT state. After that, the CT state can also dissociate. This state is usually referred as charge separated state or CS state. And finally, these charge carriers can travel to the electrodes in the solar cell. The carriers are guided to an external circuit to produce electric current and consequently energy. The dissociation and recombination processes of the excitonic and CT states are key to understand the photocurrent generation in organic solar cells, and this constitutes the main focus of my thesis. So, how can I study these processes? During the last 3 months, I have worked with two techniques frequently used in device characterization. First, I use current and voltage measurements in the form of JV curves at different temperatures and light intensities. The material measured is a specific high-efficient organic blend that you can see on the left-hand side of the screen. This material is usually called H2D2 for short. Additionally, I modify a grid diffusion model to simulate JV curves, whose equations you can see on the right-hand side of the screen. Despite this set of equations already seems overwhelming enough, I have to account for the presence of the CT and acetonic states in organic solar cells, so I add 2 more equations to be solved. With both techniques, I compare experimental and simulated data to infer valuable results. I take 2 different approaches to do so. First, I manually vary inputs to the model to reduce its complexity. I consider several assumptions in different scenarios. Some inputs can either remain constant with temperature or can be considered to be temperature activated or deactivated. In a second approach, I vary all the parameters over certain ranges that have been reported in literature. I simulate over 1 million results in a supercomputer at the same temperatures and light intensities as the ones that were measured for H2D2. With this, I look for solutions that can match experimental results. Then, after analyzing the results of both approaches, several limitations and conclusions were identified. Firstly, at low temperatures, the model overestimates voltage at every light intensity. Besides that, model current values at high light intensities are lower than the ones measured in H2D2, as it can be seen on the figures on the right-hand side of the screen. Apart from that, some inputs of the model have to be considered dependent on other variables than temperature, like for example, light intensity. It is also discovered that there is a direct correlation between the dissociation and recombination of both the CT state and the acetonic state. Moreover, different sets of inputs can lead to the same solution, therefore uniqueness is not guaranteed. That means that without further constraints on the assumptions, 2 different solutions generate identical results. And lastly, JV curve fitting has proved to be insufficient to ambiguously determine physical parameters of organic semiconductors with CT grid diffusion model. Then, what can be done? First, bespoke measurements have to be calculated to properly fit simulation to experimental results by detailing more precisely certain parameters. Also, different materials should be studied to not lose generality. Besides, the complexity of the model has to be further increased to account for other variables different than temperature and light intensity, for instance, disorder and crystallization, which also affect in photocurrent generation in organic solar cells. So, what has Mark learned with all these projects? With Jake, he has discovered how simple strategies can be used to reduce the cost of mini-grids. Matthias provided digital tools to enhance electrification projects. Moreover, with Paloma, he discovered the importance of stimulating productive uses of energy when electrifying the community. Camille and Anne helped SEF land on how to get easy, safe, and affordable access to water while doing it in a more sustainable way. Lastly, Mark became more aware of the viability of semi-transparent organic solar cells in solar hydrogen production and greenhouses with Wesley's insights, while I informed him about the fundamental limitations of this technology that condition its possibilities in SEF land. Our projects have tackled several issues that could potentially help to reach the United Nations Sustainable Development Goals toward a more sustainable future. We hope that this could have given Mark some insight about specific measures and procedures to improve the life of the SEF landers through technology development, in this case mainly focused in solar energy and particularly in electrification. However, this is only one of the many different topics that can be treated to fully address the issues that the people in SEF land are facing. For instance, our colleagues early this morning presented innovative approaches to decarbonize the transport sector. Later today, the Energy System Transitions Group will present different policy and financial mechanisms that can enable the transition from the current energy scenario to a more sustainable one. We hope that Mark can learn from these groups to improve the lives of the SEF landers even further. Thank you very much all for attending this conference. We hope that our theses have been insightful and interesting for all the people that is watching this presentation. Please wait with us, and if you have any questions regarding any of the projects presented, come to the panel discussion facilitated by Dr. Phyllis Sangwell, one of our solar experts at Imperial College London. Thank you very much again, and enjoy the rest of the conference.